Hello and welcome to another video. This one's going to be a little bit different. I'm going to show you how I write code formatters, the tools that I use for them, as well as a few examples of some of mine, and why I pick the approaches that I do. But anyway, let's jump into that. Before we do that, I'm going to show you a few of the formatters that I have written, and they all work in basically the same way, and we're going to use that technique to write our own silly formatter today. And the first of those is pyupgrade, or at least the most popular of those is pyupgrade, which is a tool which does a bunch of syntax rewriting, mostly to improve or start using newer features of the language. So that's pyupgrade. I've also got another tool called add trailing comma, which basically was the idea of Black, or at least a similar idea to Black, but almost 4 years before Black existed. It adds trailing commas to things. I guess here's the actual diffs of what it does. Another tool that I've written is called YesQA. It removes no QA comments that are no longer needed for Flake 8. This is another silly project that I wrote, which backported fstrings to old Python versions. It's now archived because I don't really support anything older than 3.7 now, so no reason to continue maintaining it. And lastly, Tokenizert, which is really what brings this all together, and this is kind of the magical library that I use. Magical, it's not magical, it's very simple in what it does, but it powers all of these different tools, and it is mostly a thin wrapper around the standard library tokenize module, except it adds a few little things that makes it easier to round trip between that. And you can see here's a list of some other things that I've built with that, because I guess I forgot one of them. But anyway, let me demo that a little bit real quick. We're going to set up a virtual environment. I'm going to install Tokenizert. I'm also going to install another tool called AST-Pretty, which is going to help us visualize the abstract syntax tree. Tokenize is going to deal with the token stream. AST is going to deal with the abstract syntax tree. And what we're going to do is we're going to cross-reference those two together and write a formatter by hand using that. Now, of course, there are many other ways to do this. For instance, there was lib2to3 for the longest time, which satisfied some of these use cases, which was a standard library concrete syntax tree. The difference between an abstract syntax tree and a concrete syntax tree is that the concrete syntax tree represents the source directly, whereas the abstract syntax tree is more just the programming concepts in memory and not necessarily tying one-to-one with the syntax. And so with a concrete syntax tree, you can do source rewriting while maintaining the original source, which is our goal of our code formatter here. There are a few open source open source CSTs. The most popular of them, I believe, is libcst by Instagram. And I have tried this and it works all right, but I've had problems with these third-party ones in the past. Notably, they usually lag a little bit behind in grammar changes in Python, and sometimes they will have quirks of syntax which the actual language doesn't have. And so that's why I tend to stick to Tokenizert, which just uses the Python tokenizer directly, and the standard library AST module, because it's the same it's the same parsing that the actual interpreter uses. And so I tend to find that's a little bit more reliable when writing these tools. Of course, some of these tools might work fine for your use case, so maybe this would be what you would do, but we're not going to show that today. The other thing that I found is some of those CSTs are really, really slow. For instance, lib2to3 was like almost 4 or 5 times slower than a tool that I would write using Tokenizert and AST. Okay, so let's talk about what we're going to write a silly formatter for today. And this is actually something that I had to do at work recently. This will be our target file. And what I wanted to do at work is automatically type annotate some functions, particularly ones where they didn't return a value, they didn't yield a value, etc., and they didn't have a return annotation. Or otherwise they had annotations for everything, but they forgot the return value annotation. The reason you would want to do this is MyPy is not going to check this, it's not going to type check this, and it's not going to type check calls to this unless it has a full signature. And so, if you were going to do print hello x, for instance, this function has a partial signature, but it needs to have this arrow none to be fully type checked. So I wanted to rewrite functions that looked like this, but avoid functions that I didn't know the return value for. So maybe like a square function which I don't know that it, oops. I don't know that it returns ints, and so I wanted to leave functions like this alone. And so the basic way that I'm going to do this is I'm going to parse the AST. I'm going to find the positions of these functions in the AST, only the ones that I want. I'm going to ignore this one. And then we're going to use the token stream to step through each of these tokens and find this sad face there and insert our arrow there. And so let's first take a look at this with AST pretty. I'm going to do no show offsets, just so that it is slightly smaller. It's still pretty big. But this is going to show us our abstract syntax tree. And you'll see here that the top level is our module that encapsulates the whole thing. And we have these function def nodes, which are going to represent our functions here. These are the ones that we care about the most. We're really just looking for these functions, and we're going to try and find all of these arguments that have annotations. Oh, this one doesn't have any arguments at all. Ones that have annotations but don't have this return annotation. So that's what we're going to look for. And then we're going to iterate through the body of the function and make sure that it doesn't have a return statement. So we'll be able to avoid functions like that. Okay, so let's write a little bit of boilerplate that's going to get us there. So we're going to need a main function. And that's 2 videos in a row I've typoed main. If name equals main, the system exit main. And we're going to use argparse to take positional arguments on the command line. Argparse, argparse.argument parser. Add argument file names and args equals star. This will allow us to pass as many file names as we want. And argparse is going to give us a little help message, which is going to be helpful as well. For file name in args.file names, we're going to do, I don't know, rewrite file name. And we'll make rewrite file return an integer as to whether it rewrote the file or not. That way at the end we have a return status that tells us if we changed something or not. Rewrite file name to int. And we're going to need the AST module, and we're going to need a few things from Tokenizert. We're going to need offset. We're going to need tokens or source to tokens, and we're going to need tokens to source. This is the round trip parts here that are allowing us to go back and forth between the source. And we are also going to need we're going to need to write an AST visitor. How are we going to do that? Let's actually open up the file and parse the AST and figure out what we need to rewrite first. Okay, so with open file name coding equals UTF-8. This particular encoding is important here. So how do I show you this? So each of these AST nodes are going to have a line number and column offset. These line numbers and column offsets are kind of fiddly in that they need to be, these correspond to the column offset if it were encoded as UTF-8, which the source might not always be encoded as UTF-8, but usually it's important to do that. And we're going to actually use these line numbers and column offsets to match up against the token column numbers and line offsets. Here's the tokenization. Note the tokenization doesn't really tell you anything about the structure of the code. It just tells you, like, def is a name token. We have a white space token here. We have another name token here. We have open and close parentheses, etc., etc. And so we're going to be using these column and line number offsets and matching them up against the column and line number offsets that we have up here. So for instance, for this first function def, it's at line number 1, column offset 0. And in our tokens, we'll be able to find this def here. I guess that one's not so interesting. Let's look at one of the other ones. G is at 5,0. So if we go to 5,0 here, we'll be able to land on this def token and be able to eventually look forward and find this. Here's our sad face there that corresponds to this bit of source here. So anyway, it's important to use UTF-8 because otherwise the offsets aren't going to line up. Because yeah, the AST always uses the UTF-8 offsets, and Tokenizert actually normalizes the offset to those UTF-8 values. Okay, anyway, contents equals f.read, and we are going to parse the AST. Tree equals ast.parse contents. Now, I usually find it is helpful to pass the file name along in here. Just in case there's a syntax error, this will point at the right file name. Otherwise, you'll get kind of a garbage error message, which isn't going to be that useful. All right, so next we need to find these function defs, and there's kind of two ways to do this. One is to use an AST node visitor, which I find is useful if we're going to have a more complicated visitor. Visitor. And this has a bunch of like visit function def callbacks that you can add, such as this. And you can write a visitor like this. I've actually shown a visitor like this in another video, which was my Flake 8 plugin. And since I've already shown that before, I'm going to show you the other approach, which is to just use ast.walk. And what ast.walk is going to do is it's going to progressively give you nodes, and we don't really care so much about the structure, so we don't need a node visitor. So we're going to do for node in ast.walk, and we're going to walk over this tree. And this is going to, let's just do this for now. This is just going to print every node as we encounter it. So if we call this using target.py, yeah, of course we have an error at the end, but you can see these are all of the AST nodes that represent this source here. And so we are actually just going to be looking for these function defs, and we're going to parse those separately. Okay, so if is instance node ast.functionDef, that means it is the node we are looking for. We also want to check a bunch of conditions on it. The first one being that it doesn't have a return annotation. Node.returns is none. We also want to check the annotations of the functions. You can say like all annotated node. We'll write a little helper function for that. All annotated. Figure that out in a second. We also want to check that we don't have a return. No return node. So if we have found all of those, that means we have found a node that we care about, and I'm just going to record the positions of this function. So found functions, which is going to be a set of offsets. So an empty set. Yeah, so this video is going to be a little bit longer than usual. Hope you don't mind. Okay, so we also need to add this def no return ast.function def, and we'll implement that in a second. But we're going to add, I'm just going to call this found. Shorter variable names. Found.add, and we're going to call offset with node.line number and node.call offset. And this particular data structure is used by Tokenizert to show where the positions are. It's really just a simple name tuple of two integers, but we'll use that later when we're iterating over things. Okay, cool. So now we need to, let's just return 0 here so that it matches those functions. Now we need to implement these two functions. Let's just start by setting them both to return true so that we can see if we find the 3 functions we expect. If we run python 3 t.py target.py, we have our virtual env activated, of course. Yeah, cool. So right now we find all 3 functions. We don't want to find all 3 functions. This one we shouldn't have matched. So we'll need to adjust our code a little bit to handle that particular case. And we can do that by doing these all annotated. I guess we could also add another function which shouldn't get hit either as well. So like this one, we didn't annotate this, so there's no point in fixing the signature because we don't know the full signature. All right, all annotated. If we go back to our AST pretty here, AST pretty, oops, we activated virtual env. I'm going to show you a little trick here. You can call AST pretty on standard in and pass it just a function here as an input string using this triple arrow here, and it'll give you the AST tree of that as well. But what I'm particularly looking for here is this argument type. And I believe it is just ast.arg. Yeah, so we're gonna actually use the same walk approach that we used here. We could, find this particular structure and this structure here and walk through it. But I'm feeling lazy today, so we're just gonna do for node in ast.walk node. I guess we should call this something else for child. If is instance child ast.arg and ast.arg or ast.annotation. Yeah. Annotation is none. So in this case, we have found something that is not annotated. So we'll just return false. And then if we don't match anything at all, we will eventually return true. So that's how I'm going to implement this function. And now we're going to do the same sort of hacky approach for the return check as well for a child in ast.walk node. And actually in my real implementation, I also checked for a couple other things like raising not implemented or not implemented error, or if the function was decorated with abstract method. There are a few other cases where I didn't actually want to add the annotation because they were intentionally stubbed functions. But in our case, we're just going to look for return. If is instance child ast.return, then we will return false. Again, otherwise we'll return true. And of course, you could add more cases here for stuff you wanted to weed out there. Cool. But now that we have added all of those, we should see, so we have 4 functions here. We should only see these 2 matching now. Has no attribute. Oh, it should say child.annotation is none. Whoops. Cool. Yeah. So now we only have the one on line 1 and on line 5 being matched, which is exactly what we want. Cool. So now that we've found our positions, now we need to cross-reference those against our token stream. And so what I'm going to do for that is parse our tokens to source, contents, and there's actually a special method or a special function inside Tokenizert that we're going to use. We're actually going to, py.tokenizert. We're actually going to loop through the tokens backwards. And the reason we're going to do that is by iterating backwards, we can modify the tokens without affecting how the loop works. It's kind of a tricky way to loop over something while it's changing. So we're going to do for I token in reversed enumerate tokens. And let's just start by printing the tokens so you can kind of see what their structure looks like. I guess we could say, like, we can also short circuit here. Like, if there are no found things, we know we don't need to do anything, so we can save this call, which is actually really expensive. If not found, return 0. So now if we run this, or has no attribute source. Oh, this should be source to tokens, of course. Silly bug. Reversed enumerate. Right, we need to import it. Reversed enumerate. And you can see we get all of our tokens here, and we'll be able to match those up by using their line number and UTF-8 byte offset, which is the same thing that we put into here. That's what this column offset is. Okay, and if token dot offset, which is a property of these tokens, is in found, then we know we're at a position in our search here that matches one of these things. Oops, did I not save? Oh no. Oh, it is found in found. Yeah, I can type. Okay, cool. So now we have found one of our tokens, and I usually find it useful to do tuple enumerate tokens to pretty print where we're at, and our position is at position 16. So if we look, we are looking at this def token. Cool. So now we want to search for it to find this colon and insert our special token there. And so what I'm going to do for that is we're going to make a small little state machine. It's going to feel a lot like advent of code here, where we're matching our parentheses and making sure that we're not at a parenthesis depth or whatever. So I'm going to say depth equals 0 while let's see, while depth or token dot source or tokens j dot source does not equal the colon. we are going to do j plus equals 1. Let's set j to I. J equals I. And we're basically looking forward for this while we don't have nested parentheses. So we want to say if tokens j dot source is in one of our grouping brackets, because you could imagine we have to treat colons specially depending on where they are. Like this colon is not our function def colon. We're specifically looking for this one, but we want to find one where it's not inside parentheses. You could also imagine, someone has a default value in here, and this could be in square brackets or anything like that. So we need to make sure, basically make sure that we have a depth 0 of brackets when we find this colon here. So that's what this depth thing is tracking here. We don't really care about what the tokens are, or what brackets they are. We just care about tracking their depth here. Depth minus equals 1. Okay, so this should get us to where j is looking at our colon. Try that again. List index out of range. Well, that's not good. Oh, of course, because I didn't do our squiggly brackets in the other direction. That would be why. Okay, cool. So now we have j, tuple enumerate tokens, and we're looking at token 25, which is our colon token. That's exactly the one that we want to modify. So we're going to change the source of this to add that arrow none in here. Do that by doing tokens j equals tokens j dot replace, and we're just going to use space arrow none colon, basically replacing out the original source, which was just a colon, with our type annotation syntax here. And lastly, we need to write out the file. Now that we've modified the token, we can take that token stream and convert it back into source. So new contents is equal to tokens to source tokens, and with open file name in writing mode, f.write new contents. And we want to return an integer as to whether we changed it. We can just use new contents does not equal contents, saying like, did we change the code? And that should allow us to rewrite stuff. Okay, let me get rid of our print. Oh, we already got rid of our print. Cool. So let's actually make a backup of our target file. And of course I would write tests for this as well, but I'm pretty confident this will work. Target.py. And by confident it will work, I made a mistake there. That's fine. Oh, why do we have this problem again? I thought we already fixed this. Well, let's debug it a little bit, see what's wrong here. Okay, so J is running past the end of it. What is the I that we're looking at? We're looking at I of 15. Interesting. Interesting. We already did this one. We showed that it worked earlier, didn't we? 15 was able to find... Oh, I see what's happening here. Yeah, so there's actually two tokens that have that same offset. So if we look at token 15 here and token 16, there's a dedent token. So we also need to make sure that we're looking at our specific token that we care about. What we need to do here is if token.source and so we're just going to filter out this empty token here. Or we can even say that token.name is equal to name. So we're specifically looking for the def token there. And that'll prevent us from doing that mistake there. Okay, so now if we rerun this again, you'll see that it printed nothing. We would probably say that it's rewriting the code. And if we look at the difference between our backup and our target, you'll see that it added our arrow none. So we accomplished our goal. But yeah, that's kind of a small example of how I've gone about writing code formatters. A little bit of demo of the AST module as well as Tokenizert. You can kind of see how I cross-reference these. If you want a much more complicated example, pyupgrade has 20 or 30 of these rewriters, and with more and more complicated rewriting approaches. The one thing that's kind of annoying about this is you kind of have to reparse the code yourself. Notice we had to deal with the brief steps here. We had to find our particular token as well as our target token and do a little bit of hand holding there. Whereas something like a CST will give you a more structured representation of the source. But anyway, hopefully you found this interesting. If there are additional things you'd like me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.